So today we're going to try to finish in this class what remains of the chapter of stochastic choice and random utility. So after we have studied the general model of random utility, we are going to study a model that we spent some time, right, in the previous lecture, the expected utility model. But now we're going to see it within the framework of random utility. Okay. So the random expected utility model, essentially, rho has a random expected utility representation if it has a random utility representation that we defined in the previous lecture, where the random utility, bold U, is such that when for any omega realization, right, this would be expected utility. So that means that each realization of the random utility is restricted to be of the expected utility form, right? So it cannot be anything else. It cannot be, of course, something nonlinear. It has to be this linear model. And of course, the cool thing here is that at this stage, we're not restricting the Bernoulli to be anything, right? So in this model, the Bernoulli utility can be convex, which means risk-loving, can be concave, which means risk-averse, and it can be linear, right, which means risk-neutral. So the U is completely unrestricted, the small U. And as you realize, what is really happening is that in each realization of the random utility that this consumer has, you have different Bernoullis. So remember that the Bernoulli is capturing the risk aversion. So you can also think of this model as a model of random risk aversion, okay? So imagine a consumer. So remember that random utility has two interpretations. The first interpretation, which is the individual stochastic choice interpretation, in this world would be that a consumer, say myself, is endowed with several risk aversion levels, right? Sometimes I like to take risks, right? Sometimes I hate to take risks, right? And then there is a distribution over those moods, right? And then essentially the random expected utility is describing that. Now, the second interpretation, as you remember from the previous lecture, is the population interpretation, right? So in a cross-section of individuals, say investors, right? Each individual is endowed with a level of risk as captured by a Bernoulli, right? And the distribution of preferences, right, is capturing that, okay? Which is heterogeneity on risk aversion as captured by heterogeneous Bernoullis. Do you understand the two interpretations? Okay, good. Yeah, and same here, you have this population of investors. You may have some mass on population of a certain type, which is very risk averse, and some other mass on the risk-loving guys, right? And essentially, you can describe this by means of a distribution of preferences, okay? Now, the thing we're gonna do with this random expected utility model is that we're gonna study its characterization. So the same thing we did with the logic model, right? So remember what happened with the logic model? The logic model was the easier model ever. So we derived this implication, which was the IAA, right? And the IAA basically restricted the odds of the probability of choice of two items in a given menu. These odds should remain the same as I change the menus, right? Now, if I start with the random expected utility model, then I'm interested in what assumptions or implications does this model has, right? And so I'm going to present them next. So first of all, I'm going to describe a preliminary definition. This is called menu expansion. So essentially, you take a menu of alternatives, which here are lotteries, and this is menu capital A. And then when I say I expand it by mixing it with lottery Q, by a parameter alpha, it essentially means that I'm going to create a new menu, right? That is going to contain all mixture lotteries, all mixed lotteries that are the alpha times P prime plus 1 minus alpha Q when P prime belongs to A. So essentially, I created a choice set that is the result of taking lotteries in the original menu, right? And then mixing them with parameter alpha with a third lottery Q, okay? Do you understand the operation? So this new menu, right, is basically the result of combining or mixing every lottery inside the original menu A with the third lottery Q here, okay? Do you understand? This is called menu expansion. So this is gonna be key for defining my assumptions next. So remember that we had this independence axiom in the expected utility world, right, for the deterministic case. So who remembers this? This essentially was saying that if I take P and Q, and P is better than Q, right? Then if I mix it with a third lottery R, then if the consumer already revealed to me that P is better than Q, the mixture of P with R and Q with R will not change the ranking, such that alpha of P plus 1 minus alpha of R is still preferred to alpha of Q plus 1 minus alpha of R. Do you remember, right? So we're gonna try to propose the analogous axiom to the independence axiom, but for the world of random utility. And this condition is essentially called linearity, right? And this is telling me that for any alpha, right, and any P lottery and any Q lottery, we can take essentially this menu expansion, right, such that I create this expansion of the menu A with the lottery Q, and then the probability of choosing lottery P inside menu A is gonna remain stable as I mix P with Q, right? And then I compare it with the other alternatives in the expanded menu, okay? So you can see that essentially I'm doing the independence axiom, right? But I'm doing it in this stochastic world. So remember that the restriction here is that every individual, for each realization of omega, they have expected utility behavior, right? So that means, right, that each individual here will satisfy the independence axiom. So what I'm saying here is if I take the menu of A, I mix it with Q, and then I take the mixture of P and Q, then of course the probability of choosing P in the expanded menu will be the same probability as choosing P in the original menu. Do you agree with this statement? Do you see how this follows from independence?
Can you please repeat, Professor?
Yes. So remember that, so let's go back to the independence axiom, right? And the independence axiom said that if I take P better than, say, lottery Q prime, right? And then I mix it with a third lottery, say Q, right? Such that I obtain alpha of P plus 1 minus alpha of Q, right? This has to be better than alpha of Q prime plus 1 minus alpha of Q, right? So it means that if I mix it with this third lottery, it won't change the rankings, right? So this condition is telling me exactly the same thing, but for the world of random utility. Why? Because it's telling me, look, if I compute the probability that lottery P is the very best, right? Menu A, right? So that's essentially the probability of the event that P is better than any other lottery Q prime inside capital A, right? Then if I mix all these lotteries, right, with the third lottery Q, nothing should change, right? Every ranking should remain the same. Hence, since it is exactly the same event, right, the probability of the same event is the same probability, right? It is the same event, the probability of the same event is the same. Hence, you know, the probability of the expanded menu of the mixed lottery P and Q is the same as the probability of the original P in the original menu. Okay? Great. So essentially, you know, this is the main axiom, but turns out that this is not the only axiom. So we're not gonna get as easy as the case of the IIA logic, okay? So it turns out that on top of independence, there is going to be more axioms required, okay? And it's random utility, so it's definitely a little bit harder. So the other axiom that is required is this axiom of regularity. This is actually a very important axiom because remember that expected utility is a special case of general random utility maximization, right? So we know that the general model is not restricted, of course, in terms of what kind of utilities we have. So now I'm going to ask you the following question. So I'm going to ask you to read this axiom with me. So regularity says that if I take and fix an alternative X, and then I consider two menus, capital A, which is bigger, right? Is smaller than capital B. So A is a smaller menu than B. Then imagine you're a random utility guy. Then this regularity axiom is telling me that the probability of X in menu A has to be greater than or equal to the probability of X in the larger menu. So what this is saying is as more alternatives enter the choice set, right? Then random utility is predicting that the probability of choice of X can only go down. So can someone explain why this should hold if you are random utility guy? So remember that for this axiom, you don't need the expected utility part, right? You just need to be a utility maximizer, okay? So can someone tell me why random utility implies regularity? Who will give it a try? Else I can ask one of you. It would be better if some of you volunteer. No. So Xin Wan, are you listening to me?
Yes.
Yes, can you please try to basically prove to me why random utility behavior will imply that the probability of choice is regular?
Because if you have more choice, given B, you have more choice. So at least you assign some probability large or equal than 0 to extra choice.
Yeah, that's exactly right. So essentially, right, if your menu has more alternatives, right, the probability of the event that X is the top of the list, right, in the given menu, so it's the best rank, the highest utility item, can only go down, right? Because remember that when more items enter the menu, right, then it is likely that there are some rankings that have some of the new elements in capital B, right, rank above X, right? So because the random utility is stable, right, it doesn't change with menu. That's an important thing. I'm going to repeat it. The key assumption of random utility is that the distribution of the preferences, right, of the utilities does not change with the menu. So as the menu expands, it remains the same probability over the same rankings, right? So now, if you basically condition the rankings to just menu A, there are less alternatives. So there will be some rankings that have some item in capital B. Let's call it item Y. So it will have Y above X, right? With positive probability. But because Y is no longer present in A, right, in capital A, then of course the probability in the smaller menu of choosing X will grow up, will only grow, right? And we're saying the same thing, right? When the menu is smaller, then the probability of the X item will only grow. So let's take this to the extreme. Imagine the menu now becomes the singleton with only X there. What would be the probability of choosing X in the singleton menu with X? Maybe 1, right? So this is the extreme where, you know, there is only one alternative, hence you choose that alternative, right? Now, as you increase now Y in the menu, so now you have X and Y. Now there will be some rankings that have Y over X, right? So now part of the mass, right? So it will be the probability of choosing X will be less than or equal to 1, right? If you now introduce a third alternative, X, Y, and Z, then again, there will be some rankings that have Z above X, right? Hence, the probability of choice can only go down weakly, right? It can only be also that why we allow for equality and not only a strict inequality is essentially the case that we're also covering here deterministic utility maximization. Because if, remember that deterministic utility maximization is a special case of random utility maximization. So imagine there is positive mass and in fact mass of 1 in a utility that always ranks X above everything else, right? Then even if you change the menus, right? So you first have menu X, then menu X and Y, and then menu X, Y, and Z. The probability of choosing X will always be 1, right? Because this is deterministic utility maximization. That explains the equality. But essentially, right, the strict inequality will happen when you have positive probability over all possible rankings, okay? So when you have 2 alternatives, either X is above Y or Y is above X. When you have 3 alternatives, there are 6 possible rankings, right? And from those, in half of them, X will be above Y. From the 3 rankings will be such that X is above Y. And then in the other 3, it will be such that Y is above X, right? But if you introduce a third alternatives in these 6 rankings, of course, the probability of X being first only corresponds to 2 possible rankings out of the 6, right? So if you have positive mass in every ranking, you will quickly realize that the probability of choosing X can only decrease, okay? Strictly, in the strictly positive mass for every ranking. So of course, in the fully general random utility, we don't need to assume that you have a deterministic utility, or you don't need to assume that there is positive mass in every ranking, right? In fact, it can cover both cases, right? Hence, we have a greater than or equal to sign here displayed. So everyone is happy with the regularity assumption. And also, I want you to realize that the regularity assumption is actually the random utility analog property of the warp of the weak axiom. Do you see why? So another way to see warp, the weak axiom, right, is that if you had some alternative chosen, right, in a large menu, right, say V, capital V, and then if you decrease the menu, right, the choice correspondence has to contain still X, right? Because when you reduce the menu, right, these possible desirable things disappear, right? Hence, if X was chosen in the larger menu, X has to be chosen in the smaller menu, right? This property is historically called the contraction property, right? And now this is implied by the weak axiom of revealed preference, okay? So yet again, the regularity property is this stochastic version of the contraction property, okay? Which is implied by the weak axiom, okay? So, so are you happy with this? So essentially, right now we have 2 axioms. Regularity is the analogous of the weak axiom of revealed preference, right? Or contraction, to be more precise. And linearity is the analogous of the independence axiom in the world of expected utility. Okay? Are you happy with these 2 assumptions? Okay? Great. Now, so there will be 2 more properties that we require for fully characterizing the expected utility in a random world. And we're just trying to understand why these axioms are implied by the random expected utility model, right? This will be the main objective of this subsection. So now, in order to introduce the next property, I'm gonna need some diagram. So in particular, the menus in this particular part of the subsection are gonna be allowed to be of different shapes, but some of them will have, for instance, a very polygon type shape. So in this polygon type shape, we're gonna basically identify what is an extreme of a choice set, right? So in the extreme of the choice set, essentially this polygon type of menu, for instance, would be these points that I actually draw, right? So in the very boundaries of the polygon, right? So the polygon is a choice set, and these points here are the extremes, okay? Now in this world, right, this being the choice set, how does it look to have a expected utility in difference curve? So the expected utility in difference curve, because it's linear, will look like this sky blue lines, okay? And as I progress in the direction of the red arrows, it means that the utility is higher, right? So as I go through this polygon, which is the choice set, what will be the maximum point? This red dot here, right? So essentially what this is telling you is that, and this is a very general mathematical principle, if you maximize a linear objective function, then usually solutions are going to be in the corners, right? They don't need to be, but when you have a shape such as this polygon and you're maximizing constraint to that, a linear objective, then the solution is going to happen in one boundary solution, right? It's going to be happening in the extreme points, okay? And it is very easy to see, right? Essentially, here we are describing this graphically, right? Linear indifference curves, right? they are progressing in the direction of the red arrows, where they're going to find their maximization point in the boundary points of the polygon shape choices. Do you agree? Okay. So what is the next assumption? It essentially says that the probability of the extreme points of A is equal to 1. Okay. And then again, this essentially covers the cases of polygon shape in general choices that have extremes. Okay. Hence, it's not ruling out things that are richer, right? Which are more complex. Okay, great. So now, there is a final assumption that I'm not going to state because it's too technical for this class, which is a continuity assumption, right? And it's essentially the analogous of the continuity assumption in the expected utility chapter. So this is we're not gonna define here just because it's super technical and it only works when I'm assuming that I have infinite choices. So I can also take this result to a collection of finite choices, right? And then I don't need to have continuity. But I'm just going to state the theorem by Gulam-Persendorfer, and then it says the following. So rho has a random expected utility representation, even only if it satisfies regularity, which is the warp analogous, right? Extremeness, which is the one I showed you a moment ago. Linearity, which is the analogous of independence, right? And continuity, which is the technical condition that we don't care now. So again, now we're going to formalize the necessity of the axioms, the things we just discussed informally. Now we're not going to prove it. Of course, we're not going to prove sufficiency because sufficiency requires higher technical mathematics that we're not going to use here. So the only thing we're going to be satisfied with is by taking the theorem 20 and showing that if rho has a random expected utility representation, then regularities imply, linearities imply, those two main things, right? So we will show first that
one question, we could do like a mapping between this random expected utility and the general expected utility, in which I think the expected utility was rationality plus independence. And here for rationality, we have regularity, and for independence, we have linearity.
Yeah, that's a good way to see it. That's a good way to see it. Great.
Thanks.
Yeah, so now that's a good way to see it. But now on top, we're going to add, we're going to just prove that linearity is, of course, necessary. As I mentioned to you, we explained informally that because every utility here that is realized with positive probability has a expected utility representation. So that means that with probability 1, independence should hold. How can we write this? Well, by this operation of expansion, it essentially means that the probability of choosing P in menu A is the event of choosing P in the menu A, right? Now, if I now look at the event of choosing alpha P plus 1 minus Q, right? On the expanded menu, alpha of A plus 1 minus alpha Q, right? Then these two events are exactly the same because of independence, right? So then the probability of choosing the mixed lottery P and Q in the expanded menu is the same because it's essentially measuring the same event. Agree? So by independence, right? So this is the same thing we discussed before. Now, regularity follows from the fact that if I have the probability of choosing alternative A in capital A, this is the event of choosing A in A. Now, since this event C, remember that it's either 1 or 0, right? So either you choose A in the capital A alternative, or you choose A in the capital B. You know that since B is bigger, right? If this is 1, A can still be the max, in which case this is equal. So 1 and this is 1. Or this can be 1 and this can be 0, right? Or in the case this is 0, this will be 0 for sure. So in other words, this event that is either a 1 or 0, right, will always be above the second event, which is always a 1 or 0, just because capital B has more alternatives in it, right? This is essentially the contraction property that I mentioned, an implication of the weak axiom. So if you measure basically the expectation of this indicator, measuring the event C, right? So this is an integral over this indicator, which is either 1 or 0, right? And then since the event capital A, right, is always higher than the other, then the probability of A on capital B is less than equal to the probability of A in capital A, okay? So as you can see, as Martin also pointed out, regularity follows from the weak axiom, right? And the linearity follows from the independence condition, okay? Great. Now, let's do some examples to put some flesh on this thing. So, for instance, who remembers what is a CR array? And what are basically these letters standing for? So this is the constant relative risk aversion, right? Now, this has this famous Bernoulli utility, right? Which essentially has the monetary price elevated to some power, right? Which captures the risk aversion. Now, in this particular example, I'm gonna interpret this coefficient as the randomness source, right? The source of randomness. So essentially, you can see that this is gonna be the omega, okay? So in this interpretation, the Bernoulli utility is of course random because the relative risk aversion is random, okay? So in this case, set to the power 1 minus omega divided by 1 minus omega, okay? So now when I compute the probability of some lottery in this capital menu A, this is the probability of all omegas such that the expected utility of the CR array is strictly greater than the expected utility of the lottery Q according to this risk aversion. So for instance, also to simplify things, imagine now omega follows some CDF. So I can take the integral of this event, hence an indicator function that is either 1 or 0, where the expected utility according to the CR array with omega parameter is strictly greater than the expected utility of Q with the omega parameter, right? And this is, of course, for all Q in the menu. And then I take the integral with respect to the CDF of the omega, which is the relative risk aversion. So a particular model of interest is when everyone in the population, right, has an average risk aversion that is shared across the population, right? And then you have a random shock to your relative risk aversion, okay? So this model is quite cool because then there is a common component, right, that people can, as a focus, and then they have a random shock to the risk aversion parameter, okay? Let's reflect a little bit about this. So imagine you are an investor, right? And then, for instance, in the morning, you are walking from your mode of transportation. So this is actually from a paper. So in Wall Street, a lot of people arrive close to Wall Street by ferry, train, or bus. And then sometimes they have to walk some blocks, especially if you arrive by ferry, right, from New Jersey, for instance. Then you actually have to walk some blocks, right, to your offices. So in doing so, you're gonna, be breathing a lot of air, from New York City that sometimes is very polluted. And pollution changes, and the level of pollution changes because of random variation of winds, atmospheric pressure, and other factors, right? So for instance, if there is not much wind, a lot of the smog, so basically emissions of CO2, will remain trapped, in Manhattan, in Wall Street area. If there's a lot of winds, then they're going to be taken away. So you're going to be exposed to less smog. So, in that sense, you're going to be exposed to random levels of smog. Now, random levels of pollution will affect the way you make decisions, apparently, according to this paper. So essentially, through, I guess, your brain functioning. So a lot of people that were exposed to more smog were taking more risks in that particular example. So that means that risk aversion, is shocked by some epsilon, right? And in this case, it was exposure to pollution. Second example, that actually this research is done in Ivy, in the business school. So there is someone in Ivy, I forgot his name right now. I'm gonna look for the reference after the class, where basically he's doing lab experiments where he exposes people to small doses of oral testosterone, okay? And then again, this person measures what will be the response in risk aversion and investing decisions, okay? So what is the usual finding? That people that are exposed to more testosterone orally, then they tend to respond more risk loving, right? Than people that have less testosterone, okay? of course, given orally. So the interesting thing about this research is that you can randomize the level of testosterone, right, between treatment and control. So you can divide the laboratory. Imagine you have 100 students. You can give 50 of them at random using the flipping of a coin, right? If it turns out heads, you give them, it can be either female or male, whatever they want. You can give them a pill that has a little bit of testosterone. This is used usually for supplements when people get old. But now you can give this to, to students. And then you're gonna modify a little bit testosterone level, right? In things that are only temporary, hence approved by the IRB, so the Internal Review Board, right? So this is ethically approved. So, and then of course, you're gonna be able to measure the effects of this, right? So yet again, everyone has a benchmark level of risk aversion, right? Which is formed by your upbringing, your genes, your genetic endowment, your culture, right? Your education, and then yet again, there is variation in hormones, right? So everyone has fluctuations in hormones, right? Certain foods boost, for instance, testosterone. Doing certain exercises boosts testosterone, right? And your genes also affect the level of testosterone, your age, So all of this, if you're thinking of a population, can be thought also as heterogeneity, right? But I'm thinking more of random factors such as what you ate yesterday, right? And then that's more random. So my point being that's why random utility is so important, because it gives you a general framework that tries to capture this, which is almost impossible in the deterministic framework, right? So like, for instance, having investors that have a fixed level of risk uncertainty, that's a little bit what we're assuming in the deterministic world. And that's actually very unrealistic, right? Because, it's very hard for people to have a deterministic level of risk aversion, right? So most likely it's going to be kind of a fixed level of risk aversion plus some shock, right? And then, of course, this additional level of shock, because it's so hard to understand what is the actual source of it, then we can understand it as a random shock, hence the random utility framework, okay? Any questions about this? Now, one important thing, as you realize, is that, of course, my random expected utility models are not restricted to be random CRA, right? As in essence, you can take any model of expected utility that people use, right? And make it random, right? Right now, this is a super convenient model of randomness because it has only one source of heterogeneity, right? The omega. But for instance, you remember there are modifications of the CRA allowing for more parameters of risk aversion. So you may have on top of it a beta, right? So you have a beta and an omega, and then you have two random parameters. This is still allowed in the random expected utility framework, right? So just remember that this is a very, very special case. And the general case, of course, allows for any Bernoulli utility, okay? Good. Now, okay, so we're done with the expected utility world. We're done with the logic. So now let's get serious. So now let's do what is missing. So as we study the deterministic utility framework, we in the end ended up deriving this equivalence theorem, saying that maximizing a utility function is equivalent to the GARP, right? The generalized axiom of revealed preference. Remember? That included the world, of course, but also included this acyclicity condition that essentially is a way to capture the transitivity condition, right? So in the world of random utility, we haven't done that yet. Do you understand? We're missing the analogous of the GARP, okay? Or the SARP too, because here we're not really considering indifference. We're just considering a world of indifference with mass zero, right? So there is no indifference in this world. However, there's randomness, okay? So now, let's study general random utility. And in order to understand what's coming next, which is super technical, so I'm warning you already. So the condition that is gonna come is not gonna be as nice as the linearity condition or as the regularity condition. No, it's gonna be a kind of very mathematical condition, but we're gonna try to understand it by means of an example before we go there, okay? So let's start with example 28. So the simplest possible example, of course, is gonna have a choice set of two alternatives, A and B, okay? How many possible rankings there are when you have two alternatives? Well, there are only two, right? And in fact, I can always compute the number of rankings in any given choice set, right? If I just take the number of the cardinality of the choice set, and then I essentially take the factorial of that cardinality. So if I have two alternatives, the number of rankings that there's going to be is going to be 2 factorial, right? What is 2 factorial? It's 1 times 2, right? It's essentially 2 rankings. If I have a choice with 3 alternatives, the number of rankings that are possible is 3 factorial, which is 1 times 2 times 3, which is 6, right? So it's 6 possible ways of ranking, right? So this is the way I can compute the number of rankings. For 2 alternatives, I have only 2. Is A is better than B, and in the second ranking, B is better than A. Now, what is a random utility? A random utility rule is this probability in the simplex of the set of all rankings. So the set of all rankings is going to be denoted here by capital R, okay? So capital R here, so let me even be super specific, is essentially the set of ranking 1 and ranking 2, right? So pi is a probability distribution over the set capital R. So it's putting masses over probability 1 and probability 2. And essentially what we're requiring is that the probability of each ranking is positive, right? And that the probability of ranking 1 plus ranking 2 is equal to 1. So any complaints about this so far? Super easy, right? So a random utility is just a distribution over 2 possible rankings in this world. Of course, if I have 3 rankings, it will be a distribution over the 6 rankings. Yeah, Martin?
Yes, sorry to ask, but I don't intuitively, I don't get the difference between the previous case at this random expected utility.
Yeah. So the difference is that here the rankings are not required to be expected utility, right? In fact, for instance, A and B can be anything. Which is
So
A can be.
They may be, but they are not necessarily.
Yeah, for
Okay.
sure. They may be, but they are not necessarily random expected utility. For instance, A might be a Honda and B can be, a Toyota. So in this case, I need another model, right? And this covers that.
Yeah, the general framework. Okay, thanks a lot.
Great. Yeah, it's a great question, Martin. It's sure we're a little bit jumping from domains, but the main motivation for me to covering expected utility is because the axioms of expected utility are nicer. And also we're allowed to introduce the regularity. So now we're going to go to this thing, which is mathematically hard. So sometimes, going through expected utility is a bit of a warm up, okay? Now, so now that we have done it, right? This is a random utility for the case of 2 goods, okay? First example. Now, let's go with a small, characterization. What would happen if I have 6 alternatives, right? Then I will have 6 rankings. 3 alternatives. I have 6 rankings, right? And then I have 6 possible rankings, and then I have to put a probability over the 6 of them. Okay. Now, given this, what would be the probability of choosing alternative A in menu capital A? So here, yet again, in this notation that I created for this section, right? This is essentially the expectation, right? Which is the summation of each ranking over each ranking with the mass of each ranking, the probability of ranking with a symbol of the preference of the event, hence the indicator notation, that A is strictly better than B. For all B in the menu capital A, remove the item A. So essentially what I'm doing is the following. So imagine I go right now through the class, right? And I ask you, what do you like better, Honda or Toyota? So some of you will raise your hand, right? And in fact, let's imagine from the 12 of you, 6 of you say, I like Honda better than Toyota, right? So then the probability of pi of the preference 1, which is Honda is above Toyota, will be 50%, right? And then if the probability of choosing Toyota will be the fraction of you that pick, of course, Toyota over Honda. So this is what is written here. So this pi over the probability, over the preference, sorry, is the probability or the fraction of individuals in the population that are governed by that given preference, right? In the example I gave you, right, one preference was saying Honda is better than Toyota, right? And the probability of that particular population, fraction of population was 50%, right? So the share of 50% of you like better Honda than Toyota. So that's the pie of Honda over Toyota. And then, of course, in this case of two alternatives, it's super simple because only one ranking ranks Toyota over Honda, right? Now, if I have more alternatives, such as 3 alternatives, I'm going to have 6 possible rankings, right? So if I'm now studying what is the probability of choosing A in a menu with 3 alternatives, then I have to consider 6 possible rankings. In these rankings, there's going to be a subset of those rankings that put A at the very top, right? So I'm just going to take the summation over those rankings and with a corresponding probability, mass probability of the rankings that are such that A is better than B, okay? Do you understand the notation? So the notation, the first quality is super simple, right? It's just a summation over the fraction of people that are whose preferences are characterized by the preference of the symbol, right? And that's it. And then the event that I'm measuring inside the indicator function is that A is better than B for all B, okay? Perfect. Now, this is equal, of course, a nice symbol that we can use here is this expectation symbol, right? The expectation symbol is telling me that this is the expectation of the event. Of course, it is the expectation with respect to this probability distribution, right? The phi of the event such that A is preferred to B, and then I have a wiggle or a little wave above the preference symbol, right? Because this symbol now is random, right? So I'm taking an expectation over this random element. And then of course, the random element is ranking A above B for all B in the menu, okay?
So could you replace the meaning of pi?
Yeah, pi is just, so there's 2 interpretations as usual. So the population interpretation is just the fraction of people whose choices are governed by the given preference type. So in this case, for instance, with two alternatives, there are 2 preference types, preference type 1, preference type 2, and pi measures the fraction of the population, right, that are governed by pi 1 and pi 2, right, such that the total types add up to 1. Okay, because this is a share. Okay, now the individual interpretation of randomity is essentially you are a decision maker. Now you have unstable preferences governed by a distribution pi, right? So pi is measuring the fraction of times you as a decision maker are governed by preference of type 1, right, and of type 2. Okay.
Thanks a lot.
Okay, great. So.
Sorry, Professor. I don't know, maybe silly question, but for the, yeah, when you do summation, right, and you have this pi, then I, this index, correct? So why we're putting here this I again? Can you explain?
Yeah.
So what we are assuming?
Yeah, so this I, as defined above, right, below, sorry, it's an indicator function that is essentially telling you that whenever these preferences are such that A is better than B, this is a 1. For all B, of course. And then when this is not, at least there is some B that is rank above A, right? Then this is 0. So this is a usual trick, and this you will learn more also with Nair. So when sometimes you can measure an event, right, with this indicator function that is going to tell you essentially that it is 1 if the event happens, and it is 0 if the event doesn't, right? So that means that then I have this, little indicator function, and then I can take expectations over this indicator function. And if I do that, then I'm going to end up as a result with the probability of that event. Okay.
Yeah.
Yeah. So with Nail, I think sometimes they give you in the probability class, right, an interpretation of the CDF, right, as the expectation of the indicator function, right, of the event that the value X is less than or equal than the random variable capital X, right? And then this indicator function, if you take the expectation of that, that gives you the CDF, which is f of small x, right? So that's a usual interpretation of the CDF as an expectation of the indicator of the event that, the value that you're fixing, the CDF is less than or equal to the random variable, okay? So this is doing the same. This is telling you the probability of a small a and capital A is essentially the CDF of this event, right? So the cumulative probability that A is better than B in the whole menu. So of course, this may happen for different preference types. So you have to add up over all preference types.
Yeah. So here we're just assuming that A is better than B with probability 1, but we could say also that B is better than A with probability 1, right? It's just up to us.
So yeah, that's right. But the correct way to think about it, this is formally called the indicator function, and it's not really a probability, right? It's just a function that is telling you 1 if this happens and 0 if it doesn't, right? And then, of course, you put this indicator function inside this expectation, right? Adding up over all the instances where this is 1, right? So in words, this is telling you, right? So I go and try to measure what will be the probability of you as a class picking Honda over Toyota. So then the event that I fix, right, is that Honda is better than Toyota. So if Honda is better than Toyota, according to this particular preference, this is going to be a 1, right? Then I multiply it by the fraction of people that actually hold those preferences, right? So in this fictional example I created, right, 50% of you rank Honda above Toyota, right? So I have to multiply this 1 indicator times the fraction, which is 50%, right? And that's going to give you the probability. Now, imagine you have now 3 alternatives, so it's more complex. You have 6 rankings, right? From the 6 rankings, only 2 of them rank Honda above Toyota, and then imagine you have a Mazda, right? So if you rank all of them, will be Honda above Toyota above Mazda, and then you keep going. So essentially, only of the 6 of them, 2 of them will have Honda at the very top, right? So then you have to, again, ask, and people tell me what are the fractions of people holding the preference 1 and preference 2 that rank Honda above everyone else, right? And then I essentially compute the accumulated share of people, right, holding the preference type such that it ranks Honda above the rest. And this will be equal to the probability of choosing Honda. Do you understand? So in essence, this notation is telling me something very simple, just a counting procedure, right, of different events. Any other question? Okay. So now, okay, so these 2 things are nice. And now remember that in the original formulation of random expected utility, we also have this notation using the omega, right? Which was the underlying probability space, right? And we're going to assume here that this underlying, so there is a measure of this probability space that is captured by this symbol P, right? With the probability with the double line. And then you can also write it in terms of measure theory as essentially the measure of all omegas such that they will give me a realized preference relation, right? Such that A is better than B, okay? So what is interesting here, even if we call this random utility, it is really a random preference function, right? We know by the previous chapters that if there is a utility, there is also a preference ranking that is complete and transitive, right? So we can do this without loss of generality. Of course, we're assuming that these preferences are such that there is no indifference. And besides that, it's essentially the same. Now, there is some advantages of using preference relations over utility functions, right? And they will come apparent next, but mainly we are going to be able to use preferences to derive the guard analogous, right? If we use utility, it will be very hard to do so, right? So that's why we're using this thing. Okay, any questions here? Any questions here?
Yes. Maybe you already asked this, but I don't know. Why do we take the expectation? What's the meaning of the notation of the expectation there in the?
Yeah. So essentially, because this is an equality, right? This expectation here is equal to this previous part, right? So essentially, this is the meaning if you want. So the expectation here is defined in terms of this thing I'm highlighting. So it's a summation over different preference types, right, of the event. So what is an expectation, right? In general, the expectation of a function is you take it, you put a function inside, and then you take a summation of it, right?
Yeah. What I don't get is the subscript pi there.
Oh yeah. So
yeah.
So I can delete it, but in general, so modernly people use as a subscript of the expectation operator, they put with respect to what distribution they are taking the expectation. Because the expectation operator, the expectation operator is an ambiguous operator, right? So it usually in econometrics, the distribution is fixed, right? So it's the DGP and whatever. So people usually avoid it. But in measure theory, you can take expectations with respect to different measures, right? So usually as a subscript, you clarify with respect to which measure you're taking expectation, right? So yet again, this is a notation thing, but in measure theory, you usually specify as a subscript that the measure you're taking expectation with respect to. Of course, in econometrics, it's kind of assumed that this is a DGP or whatever. So it's kind of fixed. So that's why people don't specify, okay?
Okay, thank you.
Okay. Okay, and here comes the monster. So this is a horrible condition. It's not very intuitive, but I'm gonna try to explain to you. And then I'm gonna give you a nicer mathematical condition. So again, remember that our role in this micro class is that we want to derive the testable implications of the different models we have, because essentially we want to know whether these models are good or not, right? And in the end, because this is trying to be as scientific as possible, a model of behavior such as random utility is yet another hypothesis about how humans behave. So our role as scientists is to derive the testable implications, right? To be able to know whether in real life people behave like that or not, right? So we already did that for deterministic utility maximization, and this was the GARP condition. So now we want to do the same for the random utility model. So one condition that we already derived is the regularity condition, right? Shin, he told us a very nice, discussion of how this works, right? As you add more alternatives, the probability of the original X of being picked can only decrease, right? As the other alternatives may become the best alternative. Okay, that's great. And we know that's the warp, but what is the analogous of the GARP? So here I'm gonna state the axiom, and then I'm gonna explain how we obtain it. But it's not gonna be an intuitive, but this is actually the analogous of the GARP. And in particular, because we don't have indifference of the SARP, of the strong axiom revealed preference, right? To be more precise. Hence the name, the axiom of a stochastic revealed preference, okay? So the choice probability rho, so sorry, I have to change this, there's a typo, satisfies the ASRP even only for every sequence of menus and alternatives. So the small script AK is the alternative, and capital DK is the menu. And they are indexed by K. So I just have to take a finite sequence of them, going from 1 to N, which is the length of the sequence. So this is essentially similar to remember we're studying GARP and we have a chains of cycle of size N, right? This is essentially the same, right? So I just take a collection of alternatives and menus. I'm gonna illustrate it in a bit with examples, so don't worry. But right now, try to understand abstractly what is happening, right? So now, the only restriction I have in this sequence is that the alternative AK is inside capital DK, right? And capital DK, the only restriction I have is that this is inside a choice, okay? And it is not empty. And then the axiom requires that if I sum over the probabilities of choice of AK in menu DK, and I sum over the sequence from 1 to N, then this has to be bounded above by the following alternative, the following number, which is essentially a sum over indicators. So these ones and zeros that we just discussed, the capital I, of the following event, that AK is above, according to preference R, to be in the menu DK for all alternatives B that are not AK. So in other words, AK is the maximizer of preference relation R, and then I'm taking this event that is either a 1 or 0, then I'm adding over the whole sequence. And then look at what's happening here. I'm taking a maximum over the rankings. So instead of, because I don't know the probabilities here, right? Probabilities of the different rankings is the unknown part. The thing we don't observe, as we didn't observe utility function here in the world of stochastic utility, we don't observe the pi, right? So what this axiom is telling me is instead of observing the pi, which I don't, just take the maximum over the whole set of rankings. So remember, in the case of 2 goods, there are 2 rankings. So I'm maximizing over 2 alternatives. In the case of 3 goods, there are 6 rankings, right? Then I'm maximizing over the 6 rankings. If I have n rankings, then I'm going to have n factorial, right? And then I'm going to take the summation over each sequence. And then it has to be, and the axiom requires that this summation over indicators, so either 1 or 0, is always above the summation over these probabilities. Okay. So now, this is not intuitive. So full disclosure, if you don't find this intuitive, you are not alone. This axiom is not intuitive at all, right? It's not like the GARP with a cyclicity condition. It's not actually telling you anything behavioral, right? I don't find any intuition in it, right? I had a professor of decision theory, Tomasz Stralecki, and then he said, I don't want to live in a world that only has the ASRP as the only characterization of random utility. He was very, very adamant about this, and he felt very sad that this is the characterization of the random utility. So there are people that feel strongly about this. But I see another way, right? So essentially, as scientists, we shouldn't be looking for pretty things, right? Like intuitive stuff. We should be looking at things that are mathematically implementable and also, implementable in a laboratory. So in that sense, these conditions, they're actually not crazy. You can check it in data sets and you can check in laboratories, and they fulfill the role of testing whether or not actual real stochastic choice can be generated by a random utility model, okay? So in that sense, they fulfill that role, and that's the thing we should require, not that they are pretty. Now, it would be nice if on top we have an intuitive interpretation that we can teach to students such as this class, and people feel nice about it. But I think one key issue of microtheory is that microtheorists, because they have a bias of becoming mathematicians, they like some pretty mathematics instead of useful things, right? So I believe this is an exception to the rule. So random utility doesn't have pretty math or nice interpretations. They have a computational condition that you can test, right, in a laboratory. So you can collect data in raw. So you can go to a lab, have a lot of people, compute the probability of choice of alternatives, and then compute these bounds, and then check whether this holds or not, right? Okay, now having said that, there are better ways to understand random utility, and I'm gonna do that next, not before illustrating how to test this condition for a particular sequence, okay? So brackets open. Here we're gonna check the ASRP for this very simple situation where you have 2 menus. So the whole data set is only 2 menus. You have menu capital A and B, menu B, A, B, and C. Now, let me create the sequence. I'm going to let A1 be equal to A, capital D1 be equal to capital A, A2 be equal to A, D2 equal to capital B. This is one possible sequence. There are many other possible ones. Do you understand? So this is a particular choice that I'm making to make this comparison super simple, right? But you can basically create any sequence you want by choosing any A1 and A2 in the way you want it, right? Remember
Victor,
yeah.
One question, what are you testing specifically when you test the integration of this? Are you testing whether the data that you have is compatible with general random utility or what?
Yes, exactly that. So
Okay.
I'm gonna test, and this comes in the next term, that the hypothesis that people generating the stochastic rule, the stochastic choice probability raw, is generated by a random utility framework. So there is a distribution pi over rankings, right, that generate this probability by means of this expectation we just described, right? So it turns out that this axiom of stochastic repeat preference is the necessary and sufficient condition. So it's exactly analogous of the SARP for this stochastic world, okay? So it's gonna be the necessary and sufficient condition for the row being generated by a random utility rule that is general, right? We are not assuming expected utility anymore, okay? So now, in order to check the ASRP, in fact, I have to check all possible sequences, right? Right now, I'm just gonna do a particular sequence to illustrate how to check one of the inequalities of the ASRP. So take 2 menus, capital A, which contains small a and small b, capital B, which contains small a, small b, and c. define one sequence out of many possible ones. That is A1 is equal to A, capital D1 is equal to capital A, A2 is equal to A, capital D2 is equal to capital B. And then I'm going to compute the following. So take the row of D1 of A1 plus the row of D2 of A1, and this has to be less than or equal to the max over these two quantities. First, the event that A1 is greater than A2. Why? Because the first menu only contains essentially. So here, one thing for sure. So this is wrong. So this thing here, A1 has to be better than B because the first menu only contains A and B. And in the second menu, right, A1 is better than an AJ, right? An AJ contains, of course, a B and C, right? So now there are two possible rankings, and then I'm taking the maximum over these rankings, right? So in particular, I'm gonna make it even more explicit, right? So there is no confusion. So this ranking is gonna be ranking 1, and this ranking is gonna be ranking 2, right? And I'm gonna make it super explicit so there is no confusion. I don't like the old notation I had. Okay. Okay, that's it. So there are two rankings, ranking 1 and ranking 2. And the first ranking is telling me that A1 is better than B. And the ranking 2 is telling me that A1, which is A, is better than B and C, hence the top, right? Okay, great. What other event do I need, by the way? So I also need the event. Let's make this complete. Of the event that A1, right, is better than, so this is according to preference 3, better than C and better than B, okay? And this will be taken over the ranking 1, 2, and 3. So I'm just expanding this so the notation is even more explicit, so there is no confusion, right? Okay, now let me take a particular probability that I'm inventing out of my mind. So the probability of A1 D1 is equal to 1/2, and the probability of A1 of D2 is equal to 3/4. So what is important here? So D2 is a bigger menu, right? Yet the probability of A1 is above the probability of A1 in D1, right? So 3/4 is higher than 1/2, hence this violates regularity, right? Now, importantly, right, because I'm just checking one condition, the axiom requires that I check all possible sequences, right, in order for random utility to be detected that it fails. So this data set, in other words, fails random utility. If I were to check all possible sequences created in this data set, then I will essentially, at some point, reject one of these inequalities. So some of them will fail. However, by checking this particular inequality for this particular sequence, then it turns out that it actually passes. Why? Because if I'm maximizing over these preference types, right? So then essentially, I'm going to have that I'm summing up, and then I'm choosing one preference relation, right? So from all of this, actually doing it correctly, this is a, let's do this again. Okay. So let's erase this so we can do it ourselves. So let's do this example from scratch so everyone is able to see what's happening. So I invent this data set that fails random utility, right? Because it violates regularity. Namely, rho for A1 on capital D1 is equal to 1/2. And then rho of A1 in D2 is equal to 3/4. So this is a violation of regularity, hence incompatible with general random utility. Okay. Now, take the summation over these two things, right? So if I take the summation of 3/4 over 1 1/2, right? Essentially, I will have here 5/4, right? Do you agree with this? So I'm just, putting in common denominator and adding up. So it's 3 + 2, 5, okay? Now, let's go, this is checking the left-hand side. So let me put this here. Okay. Now let's compute this other term. Okay. So remember here, there are 3 possible rankings, right? There is always the ranking that puts A on top. Remember, A1 and A2 are the same. So this would be A2 for sure. Sorry about that. But A1 and A2 are the same. Okay, so to avoid confusions, I'm changing notation, but remember A1 and A2 are the same. So in that sense, it wasn't wrong, but it's better to have it very clearly. So now, if I'm maximizing this summation, I have to pick one of the rankings, right? So ranking 1, ranking 2, or ranking 3. So these rankings are not repeated. So essentially, this number will always be 1. Because if I pick, for instance, ranking 1, right? So ranking 1, essentially here, right, will give me this condition here, which is 1, right? Or this condition here, of course, will be 0, and this will be 0, right? If I choose ranking 2, then this will be 1, this will be 0, this will be 0. And if I choose ranking 3, this will be 1, this will be 0, and this will be 0. So this condition here would be equal to 1, right? Now, this has to be above. However, I have here that 5/4, right, is above, in fact, strictly to 1. So creating a violation of this inequality, okay? So this data set is not random utility, right? We have here one verification of this, okay? Now, in general, right, so this condition is very hard to check, mainly because you need to check all sequences, right? So right now we did it for 2 menus, and this is one of the possible combinations. What is another combination? For instance, A1 is A, A2 is B, and then of course you can index now the menus by A and B again. This is another combination. Another combination is A1 is A, A2 is B, and then the first menu is A, the second menu is B. And you can keep playing. So you can see there are many inequalities to be checked. And this is the simplest case, 2 menus, 3 alternatives, okay? As menus grow and alternatives grow, this condition becomes very hard to compute, right? Now, so before proceeding, I want to show you the following. So, and then let me do this by means of the iPad. So let me go quickly to the share screen of the iPad, and then we're going to try to understand the additional feature of the random utility, which is using a set of linear inequalities. So remember a little bit in our example of the GAR, we had in the chapter 3 this nice condition about the Alfred inequalities, right? So Alfred inequalities, of course, will provide us with a computational or feasible way of doing the analysis of deterministic utility behavior. Now, in this world, right, we need to have some form of give me a second that I'm trying to connect now to the iPad. So, a more computational inequality that could serve to use it in a computer. The condition I gave you wasn't great because it's computationally very hard to check. So right now we're going to understand the following condition when the iPad connects. So can you see my iPad? You can see the white screen, right?
Yeah.
Cool. So now let's understand how the probability of choice is formed through a linear system of equations. Okay. So yet again, say I have 2 alternatives, A and B, right? And then here I have 2 possible rankings. A is better than B, and B is better than A. Okay. So 2 possible rankings. Okay. Now I have my data set, which is gonna be called rho, and I'm gonna put it inside a big vector, right? And this is gonna collect the probability of choice. I'm gonna define 2 menus. Here, I'm gonna just put the probability of A and B here. And for simplicity, I'm gonna have menus B which is equal to just the singleton A, and menu C, which is equal to the singleton B. Okay. Now I'm gonna collect these probabilities inside this. So probability of A, the probability of B in A, the probability of capital V of A, and the probability of C of B. Okay. So this is a vector now. Okay. So rho is a vector collecting the whole data set. So rho of capital A of the alternative, the small a, rho of capital A of the item, small b, rho of capital V of A, which is 1, and rho of C of B, which is 1 as well. Okay. So this is a super trivial model, right? So it's just essentially giving you a vector of the simplest possible DGP. Of course, if I have now a choices with ABC, this will be a longer vector, right? But for the purposes of the class, I'm going to do the simplest thing possible, right? It's already very complex. Everyone understands what's going to be this rho thing here now? It's going to be the vector of everything, right? Okay, great. Now, I'm going to move screens. Okay, ready? So now I'm going to do the following. So I'm going to write the following system of equations. So I'm going to write rho, right? Which is equal to rho of A, rho of A of B, rho of B of A, rho of C of B, right? And this vector is going to be equal to a matrix. Okay, this is the key. So I'm going to open a big bracket and make a matrix here. This matrix is going to have as columns ranking 1 and ranking 2. Okay.
Could you please show again the vector for rho?
I already wrote it again here.
This is the same. This is not B.
Yeah. No,
Okay.
no, this is rho. My
Okay.
That's why I typed this.
Okay.
Yeah. So now here, right? What I'm gonna do is I'm gonna define the columns as follows. So here, the column is gonna be the sequence of A capital A, right? This is gonna be B capital A. This is gonna be A in B, and this is gonna be B in C. So the columns of this matrix are gonna be just the pair of alternative menu. So the first row being a small a capital A, the second row being a small b capital A, the third row being a small a capital B, and the third row being a small b capital C. Remember, C and B are just the singletons, right? So this is probability 1 here. So this here is probability 1, and this here is probability 1, right? For simplicity. Now, with this in hand, right, I'm gonna do the following. So what is gonna be inside the matrix? So I'm gonna take the preference relation, and remember that the first preference said A is better than B, and the second preference said B is better than A. And then, according to this, I'm gonna essentially put a 1 or a 0. So if A is in the top of capital A, so according to preference 1, is A the best alternative in the menu A and B? So let's go back to this. A is better than B, right? And the menu A has A and B there, right? So this first entry of the matrix is gonna be A1, okay? Now, let's go to the same row. So now the event that A is the best according to preference 2 in menu capital A, of course, ranking 2 says that B is better than A. So in the second entry, in the first row, second column is a 0, okay? Okay. Now let's do the same below. So you can see that according to preference 1, the fact that B is at the top is 0, and let's do a better 0. And according to preference 2, this is 1, okay? Now for the B and C, because it's a singleton, if I use preference 1 or preference 2, it doesn't matter because there is only one alternative, right? So it's always going to be 1, and the same thing here, okay? So this is the matrix, okay? Now, in order for this system of equation to be well formed, there's gonna be here the unknown, pi 1 and pi 2, right? So what are the sides of all of this? So this thing here is size 4 times 2, right? This is size 2 times 1. So the multiplication of these objects is 4 times 1, right? And the row vector here is 4 times 1. Okay? Everyone understands the system of equations? Now, important thing. This is data. Okay? So rho is the data I observe. This is the stochastic choice of consumers. Okay? I want to know whether this stochastic choice of consumers comes from a general random utility, right? So this system of equations is telling me a way to do this immediately. I have to compute this matrix, the deterministic matrix of ones and zeros. It's going to be 1 when, according to the column that is a ranking preference order, the row that is going to indicate that the item paired with a menu, according to that menu and that preference order, is the small item A the top or the best alternative, the preference maximizing alternative? If it is, then you write down a 1. If it is not, if it isn't, then you write down a 0, right? And then you do this, so this matrix you can compute yourself without knowing the data. So this matrix is known to you. You can compute it. And then there is the unknown. So this is the model. Okay. So this is the known object. And then essentially to test whether this data is compatible with a random utility framework, the only thing you have to do is to check whether this system of linear equations has a solution, okay? So for this known coefficient matrix of ones and zeros, is there a pi, which is unknown, right? Such that it generates the data in the left-hand side, okay? If there is a pi that generates the data in the left-hand side, so the model is in the right-hand side and the data is in the left-hand side. If there is a model in the right-hand side that generates the data by means of this known matrix of coefficient matrix, then random utility is not rejected. And in fact, there is a random utility rule, pi, that generates the data. If there is no solution to this system of equations, then you have rejected random utility, okay? Do you understand this? This is super important. This is essentially the content of the theorem I'm gonna write next. And but as you can see, random utility is super simple in the sense that it is essentially a system of linear equations where you have this unknown coefficient, which is the probability over different preference types. And then you form this matrix, which is a coefficient matrix, computing what would be the prediction of each preference ranking of behavior, which is a 1 or a 0, right? According to each event. So in the will the alternative small a be chosen in capital A in the first row? According to the first column, which is ranking 1, the answer is yes, it will be a 1. Now in the position 1, 2, so first row, second column, according to preference 2, that ranks B above A, then the answer will be no, right? And then you keep going through the second row, you have the kind of mirror image answer where there is a 0 and 1. And then you keep going below, and then of course you have the full matrix, and then you can check this out, okay? Now, in the last part of the class, so let me now share again the leaks. So the main theorem of this section, the one that is gonna conclude everything, is the following. So it says, the following conditions are equivalent. First, so this is a row, of course. So let me correct this. So rho satisfies the axiom of stochastic real preference. 2, the following system of linear equations has a solution. So the coefficients matrix is going to be called now capital M. It's going to be of size n, which is the sequence size, and of columns times s. S is going to be the number of preference relations you have. And then this is multiplied by a vector of size s times 1. So this is the number of preference types you have. And this is equal to rho of n sub times 1. Now, where M is this ones and zero matrix, where the entry, typical entry Ks is going to be equal to 1 whenever AK, according to preference S, is better than all B in a menu decay. Okay? So exactly what we did in the simple example in the iPad. And then the pi is the random utility rule, right? So pi is essentially this collection of probabilities over rankings, and they are indexed from 1 to capital S. And then, of course, rho is this vector we wrote in the iPad, right? Which is the vectorization of all the data set, right? From the collection of alternatives and menus. And then pi has a restriction that it has to be a probability distribution, right? And S is the X factorial, so it's the number of possible rankings, okay? So this is equivalent, right, to essentially that there is a random utility rule, which is what Martin was asking, such that pi generates the data in the following way. So rho of A in the menu A, which is according to our notation. So we have this notation that is being used through the class, right? So rho sub A of capital A is equal to the summation over preference types according to the event that according to that preference type, A is the best, right? And then finally, there is a final condition that is presented here due to historical reasons that are called total monotonicity or total regularity. That sometimes is presented as a more intuitive condition that people don't use it much. It was invented by psychologists where essentially you can compute these polynomials that have this -1 elevated to the cardinality of the set D that belongs to this collection of sets that I'm going to describe, -C, of the row A in the menu D. And this collection of menus is going to be such that if I take all alternatives in the power set of X, such that for a given C, this is the supersets of C. So this is all the choices that are bigger than C. And then these polynomials for all such C and A will be positive, right? And this is called total monotonicity or total regularity. So from this historical condition 4, we're going to show that essentially random utility that is written in literal 3 or number 3 is equivalent to solving this system of linear equations, right? And this is equivalent to the axiom of stochastic real preference, right? And the final one is going to be left there because we're going to use it there, so sometimes it's convenient, but we're not going to prove the equivalence to this particular condition. So any question here? But this is supposed to be the
for Afia theorem.
Yeah.
Okay.
Exactly, Martin. So this is the parallel of Afre's theorem. So the condition 2 is the equivalent of the Afred inequalities, right? So this is something you can put in MATLAB, in Julia. Condition 1 is this GARP condition, right? So this is the thing that you can check by hand, but in general, it's not that easy to check. And then condition 3 is the model, right? Is that you're generated by random utility. And condition 4 is this historical condition that some people use, especially in psychology, that is the same as 1 and 2, right? So there is no benefit, but we're going to need it for a proof later. So I'm introducing it here. So essentially, we're going to focus in 1, 2, 3, and then have 4 as part of the historical reasons, right? And because it's going to be useful later on. Now, important thing. So we want to show that 3, the fact that a data set is satisfied by is generated by a random utility rule, pi, implies the axiom of stochastic real preference. Okay. So this is the first thing we're going to show. Okay. So the first thing we're going to show is that 3 implies A or B. So know that 3 holds for any sequence of AK dk for any size, such that AK is inside dk and dk is inside X and dk is not empty. We have what is the probability of the summation of rho dk of AK. So I'm just writing the probability by definition 3. This is equal to the double summation of 1 to n of the summation of all preference types from R, basically all preference types inside R, of the event that AK is the best alternative in the menu dk. And then this happens for some probability pi, okay? And this probability pi, this is essentially a measure over all possible rankings, okay? Now, notice that if I take this equality, right? And now I just write it again. So I'm just repeating the equality I wrote. So the right-hand side of the equality above. And now I maximize over all pi's. So instead of just focusing on the pi that generates the data, I maximize over all possible pi rules, right? Then obviously this is gonna be above because I'm maximizing over the pi's. So this is a fixed pi. I'm maximizing over the pi's here. Because I'm maximizing, this has to be strictly a greater than or equal to the original quantity. Do you understand? So this is a trick I'm making. Remember, I'm trying to take necessary conditions. So what is the issue with this first equality? What is the unknown part? Is the pi part. I don't know the pi, right? So instead of knowing the pi, I'm gonna take and try to remove pi from the equation, right? What is a way to do it? And I can try to maximize over the all possible pi's, okay? And in doing so, I'm gonna generate an upper bound, right? So without knowing pi, I'm gonna be able to generate an upper bound of the summation of rows in the left-hand side. So just to be clear, the left-hand side here is data. The right-hand side here is a model. Pi is the description of the model, the random utility. Pi is unknown, so it's an issue. So remember in the Afriet's theorem how we got rid of the utility function, of the gradient of the utility? This has the same spirit, right? So I want to get rid of pi. How do I get rid of pi? By maximizing over all possible pi's, okay? They don't have any restriction. They don't have to reproduce the data. I'm just maximizing over the whole universe of pi's, okay? Whole thing. And then it turns out that even if this sounds very hard, the solution is analytical and close. If you're maximizing a function, right, that happens to be linear, right? So remember this thing we studied in the expected utility world that I was maximizing the expected utility, which is a linear function, right? It produced it in different curves that were linears, right? Linear in different curves, right? So straight lines. If I maximize this over a polynomial, right? A polygon, sorry, not a polygon, then the solution is going to be an extremal solution. It's going to be a solution in the extremum. What is a simplex? A simplex is essentially a polynomial construction, right? So geometrically, it's going to have the property that's going to be characterized by some polynomial figure, a polygon figure. So, and then if I maximize this linear function in this object, I'm going to end up with a solution in the extremes. So it turns out that the solution of this problem is going to be a maximum over the deterministic rankings of the event 1 or 0. So instead of basically the pi's, the only ones that are going to be active are probabilities with probability 1 over some ranking, okay? So essentially, the solution to this problem is equivalent to solving over the deterministic collection of rankings because the solution has to happen at an extreme. So all solutions are going to have positive mass of 1 on a particular ranking of preference order, okay? So if I put all this together, I end up concluding that the axiom of stochastic reference must hold because the summation over this particular sequence of alternatives and menus has to be bounded above by the maximum over deterministic rankings of this summation over the deterministic event that AK is the best alternative in the menu decay. So now this is it. Now, as you can see, the structure of the general random utility implies this linear equality here, right? In 2. And we know that it's essentially the same as random utility, right? So this is trivial to prove. So the only part that we want to prove is the following. So using something called the Farkas lemma, theorem of the alternative. So for every linear system of equations that have the following form, m pi equal to rho, which is the one we wrote in the iPad, and then we wrote here in this theorem, then there is an associated linear of system equations, m prime times y, such as for some y, and such that if m prime y is greater than or equal than 0, it has a solution even only if m pi of rho does not have a solution. So that means that A Z P means that the inequality cannot have a solution, which implies that m pi is equal to rho. So this is a lot, but essentially what I'm telling you is the following. So if you have a linear system of equations, by the Farkas lemma or theory of alternative, there is an associated system of linear inequalities, right? And this shadow or alternative system of inequalities in this case, right? If this shadow or alternative system of inequalities does not have a solution, then this is a guarantee that the original system of linear equations with equality has a solution. In the same way, if the system of equation in the original one, m pi equal to rho, does not have a solution, then the system of inequalities will have a solution. So the Farkas lemma essentially says that you can check whether a system of equations has a solution or not by checking the mirror image question in an associated system of linear inequalities. So what the axiom of stochastic real preference is saying is essentially an application of this Farkas lemma of theory of the alternative for this case. So number 2 essentially says that random utility is a system of equations, right? So if the system of equations has a solution, then random utility holds and generates the data. Now, that means that there is an associated system of inequalities that won't have a solution. So axiom of stochastic real preference is essentially guaranteeing that the system of inequalities does not have a solution, okay? So this is more a mathematical footnote here, but what I want you to realize is that you can use this term in the following way. So in order to test whether or not random utility generates the raw data, you can use 2, right? And the axiom of stochastic real preference is more like the guard condition. So it tries to explain, an analogous of the SARP. So it's supposed to be the mathematical analogous of a cyclicity. And then, condition 4 is again this historical condition we're going to discuss. But yet again, as in the first theorem, you can use 2 as the thing you can put inside MATLAB, right? So you can go right now, get a generated data set of stochastic choice and test the system of inequalities, okay? So right now we're done with the class. I'm going to stop recording